In 2022, the James Webb Space Telescope captured images of galaxies that existed when the cosmos was just 2% of its present age. Structures so enormous they shattered every theoretical framework describing how the universe constructs itself. We thought the early universe was dim and sluggish. It was neither. It was ferocious, rapid, and staggeringly productive. Tonight, we encounter black holes heavier than the galaxies that contain them. Oxygen found in a galaxy born a mere 290 million years after the Big Bang, and a cosmological crisis that science has not yet resolved. If that is worth your time, like and subscribe. We start right now. On the morning of December 25th, 2021, a rocket launched from the Kourou Space Center in French Guiana, carrying what may be the single most intricate object our civilization has ever dispatched beyond the boundary of Earth's atmosphere. The James Webb Space Telescope tipped the scales at roughly 6,500 kilograms, not quite two-thirds the mass of the Hubble Space Telescope it was engineered to follow. But drawing that comparison, however natural, fundamentally distorts the picture. These two machines were not sequential drafts of a single design. They were built to interrogate different questions, to exploit different physics, to probe different eras of cosmic history. The distinction starts with the mirror. The James Webb Space Telescope carries a primary mirror 6.5 meters in diameter, assembled from 18 hexagonal segments each plated in gold, each weighing approximately 20 kilograms. Hubble's primary mirror spans 2.5 meters. Surface area governs light-gathering power more than diameter alone does. The newer instrument collects roughly 5 times as much light every second, but more significant than sheer collecting power is the wavelength range it was engineered to receive. Hubble was built to observe from the ultraviolet through the near-infrared portion of the spectrum. The James Webb Space Telescope operates in the infrared, from wavelengths just below the threshold of human vision out to wavelengths 28.5 times longer than the deepest red our eyes can register. That sensitivity shift is the whole story. The universe contains objects that Hubble was categorically unable to observe. The James Webb Space Telescope was constructed precisely to find them. The launch itself was, by any candid accounting, a harrowing event. To fit inside the Ariane 5 rocket, the telescope required folding. The primary mirror had to fold. The secondary mirror had to fold. A 5-layer thermal sunshield the footprint of a tennis court had to be compacted into a shape narrow enough to slot inside the rocket fairing. That shield's function is to hold the telescope's detectors at negative 223 degrees Celsius, cold enough to pick up the faint infrared glow radiating from the earliest galaxies without the telescope's own thermal emissions drowning out the signal. The warmth the shield was designed to block comes from 3 directions simultaneously: Earth, the Moon, and the Sun. Following launch, the telescope spent approximately 30 days unfolding in space. Engineers at the Space Telescope Science Institute in Baltimore had cataloged 344 single points of failure embedded in that deployment sequence, meaning 344 discrete mechanical operations where a solitary malfunction would have destroyed the mission irreversibly. There is no servicing flight available for a spacecraft positioned nearly 1 million miles from Earth at the Lagrange, 2 gravitational equilibrium point between our planet and the Sun. Hubble, parked only about 340 miles above Earth's surface, received astronaut visits 5 separate times for maintenance and improvements. the James Webb Space Telescope was dispatched to a location permanently beyond human reach. Had it failed there, it would have remained exactly where it stopped, drifting forever, accomplishing nothing. It did not fail. Every one of those 344 steps completed successfully. The mirror segments were aligned to a tolerance finer than a single wavelength of visible light. The instruments cooled to their operating temperatures. By the middle of 2022, scientific observations had commenced, and within weeks the telescope was transmitting data that its engineers and scientists characterized as exceeding their most optimistic pre-launch expectations. The central question was then what the instrument would reveal when aimed at the oldest photons in the universe, the infrared glow emitted by the very first galaxies, light that had been crossing space toward Earth for nearly 13 billion years, undetectable until this moment. That question was about to receive answers that no one had truly anticipated. Light traveling from remote galaxies carries embedded information about its point of origin. As the universe stretches and expands, it pulls that light along with it. A photon that departed as ordinary visible light from a young star forming inside a galaxy near the edge of the observable cosmos will complete its journey at Earth as an infrared photon. The more distant the source, the older the light, the greater the expansion has elongated it, and the further it has shifted toward longer wavelengths. Astronomers call this redshift. It is not a poetic device or a rough approximation. It is a direct and unavoidable physical result of the fact that the fabric of space itself has been growing during the entire time that light has been in transit. When Hubble held its gaze on specific patches of sky for days, at a stretch to generate its celebrated deep field images, it was accumulating light from galaxies that coalesced 1 to 3 billion years after the Big Bang. Past that depth, the light fell entirely outside its sensitivity window. The first galaxies to condense after the universe cooled sufficiently to permit atoms to form came into being somewhere between 100 and 400 million years after the Big Bang. Their light has been en route to us ever since. Some of it arrives this very second, each photon carrying encoded data about structures that predate our solar system by 9 billion years or longer. But it arrives as infrared radiation. And throughout virtually the entire history of modern astronomy, it arrived without being detected. Hubble simply lacked the capacity to see it. No optical or near-infrared instrument on the ground or in orbit possessed that capacity. The universe had been transmitting the record of its earliest chapter without interruption for nearly 13 billion years. And all the while, humanity was tuned to the wrong frequency. The engineering obstacles involved in constructing an instrument to receive that signal are not trivial. Infrared detectors produce their own thermal noise, which means any room temperature instrument searching for faint infrared emissions from primordial galaxies would be blinded by the heat it generated itself. That is precisely why the 5-layer sunshield exists. It is also why the telescope was stationed at Lagrange 2, a gravitational equilibrium point that keeps the sunshield perpetually interposed between the telescope and the 3 primary heat sources in our immediate cosmic neighborhood. Ground-based observatories contend with yet another problem: Earth's atmosphere, which blocks and absorbs most infrared wavelengths before they can reach any detector on the surface. The only viable solution was an instrument cold enough, large enough, and far enough above the absorbing atmosphere to receive the signal in its unfiltered state. The cosmic interval the telescope was constructed to study carries a formal designation in the discipline: the epoch of Rayonization. It refers to the period when the very first stars and galaxies ignited, and their ultraviolet radiation tore apart the neutral hydrogen fog that had blanketed the universe since electrons first bonded to nuclei in the event known as recombination. Before this epoch, the universe was opaque to most forms of electromagnetic radiation. Photons could not propagate freely through the neutral gas. Then, within the first billion years of cosmic time, the first radiation sources switched on and began carving channels of ionized gas through that fog, until the cosmos became transparent to visible light for the first time. The James Webb Space Telescope was engineered to observe that entire transition and to peer back into the darkness that preceded it, detecting the faint infrared signatures of the first structures at the moment they switched on. When Stefano Carniani, at the Scuola Normale Superiore in Pisa, and his collaborators began processing the telescope's earliest deep exposures, they were studying photons that had left their sources when the universe was younger than 5% of its current age. What those photons encoded, what they disclosed about the objects that produced them, was already contradicting accepted models before the instrument had completed even its first full year of scientific operations. The first formal scientific deep field image produced by the James Webb Space Telescope was made public on July 11, 2022. The chosen target was a galaxy cluster designated SMACS 0723, located approximately 5.12 billion light-years from Earth. That cluster was not itself the scientific quarry. It was an instrument. Galaxy clusters accumulate mass in such concentration that their gravity distorts space-time noticeably, bending the trajectories of light traveling around and through them. This phenomenon, gravitational lensing, allows objects far too dim and distant to be observed directly to become detectable when a foreground cluster magnifies and warps the light that passes behind it. The telescope was deploying the cluster as a naturally occurring cosmic lens, a magnifier capable of reaching to depths no human-built instrument could independently achieve. The resulting image demonstrated what becomes possible when you combine that lens with a mirror 6.5 meters wide and detectors capable of recording objects 100 times fainter than anything Hubble could see. The sky area captured was equivalent to the field you would hold in view, holding a grain of sand at arm's length against a dark sky. Inside that grain of sky were thousands of galaxies. Some presented as blurred streaks and arcs, their shapes pulled and distorted by the gravitational topology of the foreground cluster redirecting their light around it. Some radiated reddish hues, their original wavelengths stretched by billions of years of transit. Many had never appeared in any catalog before. The oldest objects visible in that exposure had released the light captured in the image when the universe was less than 1 billion years old. What distinguished the reaction from the scientific community was not merely the content of the image, but the conditions under which it was taken. This was a commissioning exposure released to establish that the telescope was operational and meeting its performance requirements. The SMACS 0723 field was chosen partly because it had previously been imaged by Hubble, enabling direct side-by-side comparison. Galaxies that Hubble had required 11 days to capture as barely resolved smudges at the extreme threshold of its capability appeared in the Webb exposure with well-defined internal structure. Spiral arms, luminous nuclei, color gradients betraying the presence of different stellar populations at different stages of age. The new telescope achieved equivalent depth in a fraction of that integration time and with sensitivity still substantially above what Hubble could have reached with any amount of additional exposure. The response from researchers was instantaneous. Astronomers were posting comparative analyses on public forums within hours of the image's release. Multiple observers noted that the redshifts of the faintest objects in the frame indicated they were being observed at epochs more remote than Hubble had been capable of routinely confirming. One astronomer compared the experience to putting on corrective lenses for the first time, with the crucial difference that the lenses were revealing things that theoretical models had long anticipated, but that no instrument had ever directly shown. The immediate, practical implication was that the telescope was functioning at or beyond its design specification in its first operational weeks, before any of its dedicated science programs had formally begun their observations. But the data quietly contained something more consequential than a performance benchmark. The galaxies in that exposure were not all positioned where the prevailing theoretical frameworks predicted they should be in brightness, in spatial extent, in inferred stellar mass, or in apparent age. Some of them deviated from what leading models of galaxy formation anticipated they should look like at those distances. The SMACS field was a preview. The deep survey programs, those engineered specifically to stare at the oldest and faintest objects accessible in the sky for hundreds of accumulated hours, had not yet trained themselves on the universe. The James Webb Space Telescope Advanced Deep Extragalactic Survey, known as JADES, was conceived before the telescope reached orbit and represented the most systematically comprehensive attempt ever proposed to chart the galaxy population at the earliest accessible epochs. The program was directed by Daniel Eisenstein at the Harvard and Smithsonian Center for Astrophysics and incorporated collaborators from multiple institutions, including Kevin Hainline at the University of Arizona, Brant Robertson at the University of California, Santa Cruz, and Ben Johnson at the Center for Astrophysics. The survey focused on two patches of southern sky, the Goods North and Goods South fields, the identical regions where Hubble had spent days and in some cases weeks building the deepest images of the far universe ever produced with that instrument. Targeting the same regions was a deliberate strategic choice. Every galaxy Hubble had resolved there became a calibration anchor, and everything lying beyond Hubble's sensitivity threshold became unexplored territory. The magnitude of improvement is worth pausing to absorb. Hubble required roughly 400 orbits, representing 11 days of cumulative observation, to construct the Hubble Ultra-Deep Field, an image capturing galaxies from epochs corresponding to approximately 500 to 800 million years after the Big Bang. Those galaxies appeared as faint, unresolved patches of light, their spectra almost impossible to extract, their redshifts inferred from broadband color photometry rather than measured directly from spectral lines. The James Webb Space Telescope could achieve equivalent imaging depth in a fraction of that time, and brought the added ability to record spectra simultaneously, measuring precise redshifts and elemental compositions for hundreds of targets at once through its near-infrared spectrograph. The improvement was not a matter of degree. It was the difference between knowing a conversation was occurring in a distant room and being able to identify every individual voice speaking in it. The first significant spectroscopic dataset from JADES appeared in print in January 2023 in the journal Nature Astronomy. A team coordinated by Emma Curtis Lake at the University of Hertfordshire delivered spectroscopic confirmation of 4 galaxies at redshifts between 10.3 and 13.2, corresponding to an epoch when the universe was between 300 and 450 million years old. These were direct measurements of specific emission line wavelengths at known shifts, leaving no methodological ambiguity about when in cosmic history these objects existed. At the moment of publication, they were the most distant spectroscopically confirmed galaxies ever recorded. The quantities encoded in those spectra carried an implication that team members were measured in, stating too prominently in their initial announcement. The galaxies appeared to harbor more stars, more accumulated stellar mass than theoretical models of early galaxy formation predicted should be possible at those epochs. They were not faint marginal detections at the outer edge of the expected distribution. Several were bright, with visible internal structure, implying robust stellar populations that had been assembling for longer than the models permitted. A galaxy existing at redshift 13 requires that its constituent stars began forming within the first few 100 million years following the Big Bang. Within the standard framework of cosmic structure assembly, that process was expected to be gradual and hierarchical, beginning with compact concentrations of dark matter that accumulated gas slowly enough to begin converting it to stars only incrementally. The data contradicted that picture. Larger and statistically more robust data sets were necessary before decisive claims could be advanced. But the direction of the discrepancy, starting from the very first confirmed spectroscopic detections, pointed consistently in a single direction every time. The standard framework governing cosmic structure formation, called lambda cold dark matter, had been rigorously developed over roughly 4 decades through observations, numerical simulations, and mathematical modeling. It describes a universe whose earliest structures grew from minuscule quantum density variations, amplified across hundreds of millions of years by gravitational attraction into the first coherent clumps of matter, which collapsed under their own gravity into the first dark matter halos, which then gravitationally drew in surrounding gas that cooled and fragmented into the first stellar populations. This process was characterized as hierarchical in structure, meaning that smaller concentrations assembled first and that progressively larger structures emerged over time through the progressive merging of smaller units. The model had been benchmarked against an impressive breadth of observational data: the cosmic microwave background radiation, the spatial distribution of galaxies in the local universe, the clustering properties extracted from surveys cataloging tens of millions of objects. In nearly every application, it had performed well. Cosmologists placed substantial confidence in its predictive reliability. The James Webb Space Telescope's initial year of observations introduced a systematic problem. Across independent survey programs pointed at separate sky regions across different wavelength ranges, the data consistently revealed galaxies at redshifts above 10 that were more luminous and more massive than the model's predictions authorized. The Cosmic Evolution Early Release Science Survey, led by Stephen Finkelstein at the University of Texas at Austin, cataloged what appeared to be hundreds of candidate galaxies from the first 650 million years of cosmic time. The numerical surplus was not marginal. Luminous galaxies at redshifts above 10 appeared approximately 10 times more prevalent than the standard model predicted they should be. Caitlin Casey at the University of California, Santa Barbara, co-directing the Cosmos Webb survey, addressed this discrepancy directly in public discussion. Cosmos Webb was charting the largest sky footprint yet attempted with the telescope, ultimately cataloging roughly 800,000 galaxies spanning 98% of cosmic history. As data accumulated, Casey stated openly what many of her colleagues were observing privately. The telescope was consistently producing results at systematic odds with what the models declared should be there. Since the telescope began observing, she noted, the astronomy community had been wrestling with whether the accumulating datasets were in the process of breaking the cosmological framework. The question researchers were reluctant to voice too, loudly, was whether the model itself was irreparably wrong at a fundamental level. Conservative alternative interpretations existed. Perhaps stellar mass measurements were being systematically inflated because radiation from actively accreting central black holes was being incorrectly attributed to stellar populations. Perhaps early galaxy formation proceeded through concentrated, brief, intense bursts of star production that made galaxies appear more massive than their time-averaged developmental histories would predict. Both of these explanations were theoretically permissible. Neither carried independent observational support. Both were being proposed specifically as mechanisms to preserve the model against data that otherwise undermined it. The difficulty with the conservative interpretations was not that they were inherently implausible. It was that they required the early universe to function in ways that were themselves unaccounted for by existing theory. Concentrated star formation at the required efficiency lacked any identified physical driver. Pervasive misclassification of black hole radiation as stellar light required those black holes to exist in enormous numbers at extraordinarily early times, which itself introduced a separate, independent crisis about how they arrived there so quickly. Each proposed solution to one anomaly opened another. Every patch applied to the model exposed a new gap, and the gaps were all opening in the same direction. Among the findings that compelled cosmologists to frame the difficulty more explicitly was a paper published in Nature in February 2023. Ivo Labe at Swinburne University in Melbourne led a team that processed data from the Cosmic Evolution Early Release Science Survey and isolated 6 galaxies that had formed within the first 500 to 700 million years after the Big Bang, each estimated to contain stellar mass between 10 billion and 100 billion times the mass of a typical star. For reference, the Ozite Milky Way, considered a moderately large galaxy by contemporary standards, carries roughly 60 billion such stellar masses. These 6 objects, formed when the universe had not yet reached 5% of its current age, carried stellar masses rivaling some of the most massive galaxies in the present-day cosmos. The problem was not the discovery itself. The problem was the physical constraints that, having discovered it, imposed under the standard model. Lambda cold dark matter characterizes galaxy formation as originating in dark matter halos, regions where dark matter density was marginally elevated above the mean, which grew through gravitational coalescence, attracting gas that cooled and eventually condensed into stellar populations. The maximum efficiency with which this process can convert raw gas into stars is bounded by known physics. Typical galaxies throughout cosmic history convert somewhere between 5 and 10% of their accessible gas reservoir into stars across their entire lifetimes. To accumulate 10 billion to 100 billion stellar masses within 500 million years, starting from the Big Bang, these galaxies would have needed to convert nearly every available gas atom into stellar mass at a rate that never slowed from the opening moments of cosmic history. That efficiency is not merely anomalous. Given the known physics governing star formation and the feedback mechanisms through which young massive stars and accreting black holes heat and expel the surrounding gas that would otherwise fuel further star formation, it is essentially prohibited. Mike Boylan Colchin at the University of Texas at Austin, who had spent years constructing theoretical predictions for early galaxy populations, was direct in stating the consequences. In a companion paper published in Nature Astronomy the same year, he wrote that if the mass estimates were accurate, the observations placed the Standard Model under severe tension, employing statistical language that, within the vocabulary of cosmological research, signals a genuine crisis rather than a minor calibration adjustment. Erica Nelson at the University of Colorado Boulder described the objects as absolutely wild, stating that they implied either an early universe more violent and efficient than any simulation had imagined, or a universe in which the physical rules governing stellar assembly were operating according to principles not yet identified. Later, spectroscopic follow-up campaigns through 2024 introduced partial qualifications. A fraction of the apparent stellar mass in some candidates appeared attributable to actively accreting central black holes rather than to stars, meaning the stellar mass estimates had been modestly exaggerated. Guochao Sun at Northwestern University and colleagues proposed that extraordinarily intense, concentrated episodes of star formation could account for part of the surplus. These revisions did not dissolve the crisis. They trimmed its magnitude. Even after applying corrections, the population of massive galaxies at redshifts above 10 remained approximately 10 times larger than Standard Model predictions could accommodate. The objects identified by Laba's team acquired an informal designation that proved more apt than dramatic labels typically do: the Universe Breakers. On May 30th, 2024, a collaboration of researchers including Stefano Carniani, Brant Robertson, Kevin Hainline, and Ben Johnson announced spectroscopic confirmation of the most distant galaxy ever directly measured. The object, catalogued as JADES-GS-Z14-0 in the Survey Archive, carried a confirmed redshift of 14.32. That number identifies a precise instant in cosmic history. The light the James Webb Space Telescope recorded had departed this galaxy 290 million years after the Big Bang, when the universe was approximately 2% of its present age, a time that predates our solar system by more than 9 billion years. The object was not a marginal detection barely above the eye's noise floor. It measured more than 1,600 light-years in diameter and harbored hundreds of millions of stellar masses in stars alone. Robertson stated at the time of announcement that the team could have recovered this galaxy even if it had been 10 times less luminous than it actually appeared, implying that equivalent or larger objects may be waiting to be found at even greater depths, potentially within the first 200 million years after the Big Bang. The confirmation of a bright, structured, massive galaxy at such an extreme look-back time was remarkable as a standalone achievement. Then came the follow-up analysis. In March 2025, joint observations combining the James Webb Space Telescope and the Atacama Large Millimeter Array, the radio telescope network deployed across the Chilean desert, detected a specific chemical fingerprint in this galaxy: oxygen. The presence of oxygen in any object in the remote universe carries an implication that is unambiguous and admits no convenient, alternative explanation. Oxygen is the third most abundant element in the cosmos overall, but it is not a product of the Big Bang. The initial nucleosynthesis event produced primarily hydrogen and helium, with trace quantities of lithium. Every oxygen atom in the universe was manufactured inside a stellar interior and dispersed when that star exhausted itself and died. either by releasing its outer envelope gently at the close of its life or by detonating as a supernova. For oxygen to be detectable in any galaxy, that galaxy must have already hosted complete generations of stars that ran through their entire life cycles and perished. The timeline implied is staggering. Massive stars, the variety that detonate as supernovae and seed their surroundings with oxygen and heavier nucleosynthetic products, live for roughly a few million to a few tens of millions of years. But before any of them could have existed inside JADES-GS-Z14-0, a first generation of stars had to ignite, and those stars had to complete their full lives and die, chemically enriching the surrounding gas before a subsequent generation emerged to carry that chemical inheritance forward. Every step in that chain had to be completed within the first 290 million years of cosmic existence, because that is the epoch at which the James Webb Space Telescope recorded the chemical signature. Under the models current before this telescope began operating, 290 million years after the Big Bang was barely beyond the predicted onset of star formation itself. The very first stars were theoretically expected to begin appearing somewhere between 100 and 200 million years after the Big Bang. That means the complete progression from first stellar ignition to multiple generations of stellar birth and death, to oxygen-enriched interstellar gas, to a fully assembled galaxy harboring hundreds of millions of stellar masses, had all been compressed into an interval that earlier models had characterized as barely sufficient for the sequence to begin. Robertson described the result as completely unanticipated. That word is an accurate characterization of the scope of theoretical revision it demanded. The parallel impossibility that arrived alongside the early galaxy mass anomaly came from an entirely different class of object. Supermassive black holes, the compact engines residing at the centers of galaxies, with masses ranging from millions to billions of times a typical stellar mass, are not exceptional objects in the contemporary universe. The Milky Way harbors one at its galactic center, Sagittarius A star, with a mass of roughly 4 million stellar masses. The most massive galaxy clusters host central black holes exceeding 10 billion stellar masses. Their presence is so standard that modeling the dynamics of any large galaxy without incorporating a central black hole would be considered incomplete. The problem the James Webb Space Telescope introduced was temporal. Assembling a black hole from the stellar seed that forms when a massive star collapses at the end of its life to fully supermassive proportions requires time. The physical ceiling on that growth rate is the Eddington limit, which quantifies the maximum rate at which a black hole can draw in surrounding material before the radiation produced by that infalling matter generates enough outward pressure to push away its own fuel supply. Sustained growth at the Eddington limit over hundreds of millions of years represents the fastest physically credible pathway to supermassive proportions. Even under those maximum conditions, building a black hole of 100 million or a billion stellar masses from a stellar remnant seed takes a span measured in hundreds of millions of years, requiring conditions that remain favorable from the earliest possible moment without interruption. The telescope was finding them at epochs that precluded even that explanation. Roberto Maiolino at the University of Cambridge and collaborators published results in Nature in 2024 confirming the detection of a black hole at the center of a galaxy named GN-Z11 at a redshift of 10.6, corresponding to approximately 400 million years after the Big Bang. The black hole's mass was estimated at 1.6 million stellar masses, accreting roughly 1 stellar mass worth of material every 5 years. A separate detection combining data from the Chandra X-ray Observatory and the James Webb Space Telescope identified a black hole between 10 million and 100 million stellar masses at a redshift corresponding to roughly 450 million years after the Big Bang. The more profound crisis emerged from a class of objects the telescope began recording in large numbers, and that received the informal designation Little Red Dots. Jorrit Matthey, at the Institute of Science and Technology Austria, and colleagues characterized this population systematically in 2024. The objects appeared compact, with spectral energy distributions shaped like the letter V. Their central, black hole masses ranged from 1 million to 100 million stellar masses. In the present-day universe, the mass of a central black hole constitutes roughly 0.1% of the total stellar mass of its host galaxy. In the little red dots, that ratio reached 30% or higher, a factor of 300 times the relationship established from observations of the nearby universe. The black holes in these objects did not merely contradict the model by growing faster than expected. They appeared to dominate their host galaxies in a proportion that the entire theoretical architecture of galaxy formation contained no mechanism capable of producing. Matthey stated explicitly that his team was unable to interpret the light they were recording from these objects. 341 objects catalogued, and the theoretical community could not reach agreement about what any of them fundamentally were. The little red dots occupied a category with no clean parallel in the local universe. They appeared at redshifts between 4 and 8, an epoch spanning roughly 600 million to 1.3 billion years after the Big Bang. And they were between 10 and 100 times more prevalent than any model had anticipated. Each one contained a central engine whose mass exceeded that of the surrounding stellar population by ratios seen nowhere in the present-day cosmos. The observations were not in question. The interpretation was. The first proposed resolution invoked a mechanism called direct collapse. Within the standard framework, black holes originate from the remnants of expired stars. A star 20 times the mass of the Sun lives for approximately 10 million years, and then collapses, its remnant core potentially forming a black hole of several stellar masses. Growing from there to 1 million or 1 billion stellar masses through sequential accretion takes significant time. But a theoretical alternative existed. Under specific physical conditions in the early universe, a massive cloud of primordial gas might collapse gravitationally into a black hole without passing through a stellar phase at all. These direct collapse black holes would arrive with initial masses of 10,000 to 100,000 stellar masses, providing a substantial head start over stellar remnants. The conditions required for this pathway were plausible in the radiation-saturated, high-density environment of the early cosmos, but they were also quite demanding. Producing direct collapse events in the abundance needed to account for 341 catalogued objects strained the mechanism to its limits and arguably beyond them. The second proposed resolution demanded black holes capable of growing faster than the Eddington limit permits. Super-Eddington accretion is not categorically impossible. Numerical simulations demonstrate that under specific geometries of surrounding gas, a black hole can temporarily exceed the Eddington rate by factors of several. But the little red dots appeared to require sustained growth, at those elevated rates across hundreds of millions of years, under conditions that would need to remain continuously favorable over time spans vastly exceeding any episode modeled in simulation. Furthermore, a black hole accreting at 10 or 20 times the Eddington rate would radiate sufficient energy to disrupt and destroy the galaxy surrounding it. Yet these objects showed concurrent indicators of active star formation. The physical mechanisms required to permit one process while enabling the other remained entirely unidentified. A third interpretation attracted fewer proponents but resisted dismissal. It invoked primordial black holes, objects that would have formed directly from density fluctuations during the very early universe, within the first seconds following the Big Bang, predating the existence of any star. Primordial black holes had been theorized for decades and proposed as candidates constituting at least some component of dark matter. If they existed in sufficient abundance and with sufficient initial masses, they would provide seeds of a scale no stellar remnant could match. The obstacle was that no direct observational evidence for primordial black holes had been established, and the conditions required to produce them in the required numbers were not well constrained by any existing theoretical framework. What Matthey and colleagues had identified was a systematic challenge to the entire account of how the early universe built its first large-scale structures. The little red dots were 10 to 100 times more numerous than anticipated. Each harbored a central engine outmassing its stellar population by proportions observed nowhere nearby. The researchers studying them stated with the precision available in scientific discourse that they could not explain what they were examining. A puzzle had become a crisis of foundational comprehension. By the close of 2024, a coherent pattern had consolidated from the accumulating evidence that individual findings had only partially revealed. The James Webb Space Telescope had been conducting science for roughly 2.5 years. Across independent survey programs aimed at separate sky regions and different wavelength windows, the results consistently indicated the same conclusion. The early universe, the interval from roughly 100 to 700 million years after the Big Bang, was not the gradual, measured awakening that the Standard Model had depicted. It was something more rapid, more concentrated, more chaotic, and more chemically sophisticated than any theoretical architecture developed before this telescope had been designed to expect. Consider the constraints the data simultaneously imposed. JADES-G-S-Z 14-0 harbored oxygen at 290 million years, requiring that complete stellar generations had already lived and died before that moment. The 6 galaxies identified by Laba's team at Swinburne carried stellar masses comparable to the Milky Way at 500 to 700 million years, requiring star formation efficiencies approaching 100% operating continuously from the very beginning of cosmic time. The little red dots hosted central black holes constituting 30% or more of their total stellar mass, requiring growth rates exceeding the theoretical maximum across a population 10 to 100 times larger than any model had predicted. Each of these results in isolation represented a serious challenge to established theory. Taken together, they implied something more fundamental. The word appearing with greatest frequency in researchers' descriptions of the early cosmos across published papers and conference proceedings through 2024 and 2025 was efficiency. The early universe appeared to convert gas into stars, assemble dark matter halos into coherent galaxies, and grow supermassive black holes at rates that violated every established constraint on each of those processes individually. The underlying question was why. 3 categories of explanation were advanced, with different degrees of theoretical support. The first held that star formation in the early universe was intrinsically more efficient than it is in the present epoch. perhaps because the gas was denser or subject to turbulent conditions that allowed larger fractions of available material to collapse into stars before feedback processes could disrupt the collapsing cloud. The second proposed that the Standard Model's treatment of dark matter was fundamentally incomplete, and that a different dark matter candidate would generate a different early structure formation history that more naturally reproduced what the telescope had observed. The third was the most theoretically uncomfortable, that the cosmological model contained an error in its description of the very early universe, possibly in the physics of rapid inflationary expansion that established the initial conditions that had not been correctly incorporated into the framework. None of these three explanations had achieved consensus within the field. All three remained under active theoretical development and continued testing against new data with each additional observing cycle. What was not contested by 2025 was the fundamental character of the discrepancy. The universe had not assembled its structures slowly and methodically from small-scale starting points. In its first few 100 million years, it had accomplished something that, viewed from our much later vantage point, resembled an almost instantaneous eruption of mass, chemical complexity, and large-scale organization. The quiet, dim, gradual cosmic dawn that theorists had modeled for decades had simply not occurred. Something faster and more violent had taken its place, governed by physics the field had not yet characterized, operating at efficiencies no model had considered plausible. And the telescope that had exposed this was barely beginning its observational program. The James Webb Space Telescope was not constructed solely to peer backward in time. It was designed to detect everything Hubble's instruments had been unable to observe at every distance, in every direction, including the vast organizational framework that structures the universe across its largest spatial scales. When its infrared detectors began charting the three-dimensional distribution of galaxies across hundreds of millions of light-years, what materialized was something theoretical cosmologists had sketched in broad terms for decades, but had never directly observed with such resolution or clarity. A three-dimensional lattice of matter extending across the full observable universe, organized into filaments, sheets, nodes, and voids, on a scale that no human analogy can genuinely represent. The cosmic web is the most extensive coherent structure in existence. It formed because the early universe was not precisely uniform. The quantum density fluctuations imprinted at the moment of inflation, minuscule perturbations in the distribution of energy that seeded the formation of everything that followed, were gravitationally amplified across hundreds of millions of years. Matter drifted along invisible channels defined by dark matter filaments, concentrating at the intersections of those channels into dense galaxy clusters, while the intervening regions were progressively drained of their contents. In two-dimensional projections of three-dimensional survey data, the result resembles a froth of interconnected threads with bright, dense nodes at their junctions and vast, dark vacancy between them. Galaxies and galaxy clusters line the filaments and crowd the nodes. The spaces separating them approach emptiness. The filaments themselves are among the most massive structures in the cosmos. A single dark matter filament connecting two major galaxy clusters might extend 100 to 300 million light-years and contain more total mass than thousands of individual galaxies combined. Most of that mass consists of dark matter that emits no electromagnetic radiation of any kind. Astronomers have no method of imaging dark matter directly. They trace its presence through the gravitational influence it exerts on the ordinary matter and galaxies it organizes, through the distortion of background light it produces through gravitational lensing, and through the statistical distribution of galaxies whose positions trace the underlying filament structure. R. Brent Tully at the University of Hawaii, whose team employed velocity measurements of tens of thousands of galaxies to map the flow of matter through the local universe, described the outcome as a network of cosmic watersheds. Just as rivers drain toward valleys and ultimately toward the sea, galaxies migrate along channels defined by the dark matter architecture toward concentrations of mass that serve as the gravitational ocean basins of the cosmos. What the James Webb Space Telescope contributed to this picture was temporal depth and spatial resolution extending into the early universe. Earlier surveys had mapped the cosmic web at relatively modest distances. The telescope's infrared sensitivity permitted researchers to trace the large-scale structure backward in time to epochs when the web was younger, more compressed, and more actively forming. Measuring with spectroscopic precision the positions and recession velocities of galaxies along filaments that had coalesced within the first 2 billion years of cosmic history. What they found was that the web's fundamental architecture had been established earlier than the models had predicted, with substantial galaxy clusters already connected by well-defined filaments at epochs, when the standard model's structure formation simulations suggested the process should still have been in its preliminary stages. The implication of the cosmic web's existence is not abstract. The filaments interconnect everything. Every galaxy cluster is embedded in a network of dark matter channels linking it to its neighbors across all distances. Matter flows continuously along those channels, drawn by gravity toward regions of progressively higher density. Individual galaxies are not isolated objects drifting through featureless space. They are embedded nodes in a web that continuously influences their trajectories, their gas supplies, their star formation histories, and their eventual fates. The Milky Way is embedded in this web. The path our galaxy follows through space, its eventual merger with Andromeda, the structure of the local group it inhabits. All of it is shaped and constrained by the dark matter filaments threading through our immediate cosmic neighborhood. Understanding our own galaxy demands understanding the larger structure it inhabits. And that larger structure, as it happens, contains regions of character fundamentally unlike the filaments where the galaxies cluster. The recognition that the universe is organized as a cosmic web carries a structural implication. Where there are filaments, there must also be gaps, vast gaps. Regions where the filaments never formed, where matter has been draining outward toward the surrounding structure for billions of years, leaving behind a near void so profound that it strains any intuition built from human-scale experience of space. These regions are called voids. The most extensively confirmed example in the known universe lies in the direction of the constellation Boötes in the northern sky, and the numbers required to describe it deserve contemplation before their implications are considered. The Boötes void extends approximately 330 million light-years across its widest dimension. It was identified in 1981 by Robert Kirshner at Harvard and colleagues during a systematic redshift survey of galaxies. Their expectation was that galaxies would be distributed across the survey volume with natural clustering variation, filaments and clusters distributed throughout. Instead, they found a region roughly spherical in geometry, containing virtually nothing. A sphere 330 million light-years in diameter, in a universe where typical galaxy separations within clusters are measured in millions of light-years. contained approximately 60 galaxies, where large-scale structure models predicted thousands should exist. Kirshner reportedly commented, after studying the data, that the void was so large he felt embarrassed to tell other people about it. The Boötes void is large enough that the entire cosmic web structure traced across hundreds of millions of light-years could be placed inside it, with room remaining. It has existed long enough, through the roughly 13 billion years since the Big Bang, to have been nearly completely emptied of its original galaxy population. Every galaxy that once populated its interior has migrated outward, drawn by the gravitational pull of the surrounding structural framework, leaving a vacuum so thorough that the handful of galaxies remaining appear to constitute a small, nascent cluster, forming near the void's geometric center, rather than a remnant of any distributed original population. The spatial scale carries a specific consequence that reshapes the imagination in a way that no catalog of distances can fully convey. Consider the following. If our solar system were positioned at the center of the Boötes void, occupying otherwise the same location relative to its immediate cosmic neighborhood, astronomers on Earth would not have confirmed the existence of other galaxies until sometime in the 1960s. The nearest external galaxies would have been so far beyond what the observational technology available to Edwin Hubble in 1925 could detect that the entire conceptual revolution of recognizing the universe's true scale would have been deferred by several decades. We would have existed as an astronomical civilization inside a near-total cosmic emptiness, with no evidence accessible through early 20th century instruments that any galaxy beyond our own had ever existed. This is what makes the Boötes void intellectually unsettling beyond its physical dimensions. It demonstrates that the universe's distribution of matter is sufficiently uneven that your location within it determines the entire empirical picture of reality that your instruments construct. The observable universe as experienced from inside a deep void, and the observable universe as experienced from within a dense filamentary structure are, in terms of the evidence they present, empirically different places. Even if the underlying physics is identical, the disturbing implication is that our own cosmic neighborhood may not be the dense representative region we have always implicitly assumed it to be. The Boötes void represents an extreme case, but researchers carefully examining the large-scale structure surrounding our own galactic position have progressively assembled evidence for something less visually dramatic but potentially more consequential for cosmology. We ourselves appear to reside inside a void. This structure is called the KBC void, named for the researchers who characterized it rigorously in 2013, Keenan, Barger, and Cowie, in a paper that initially attracted modest attention within the field. What it describes is an underdense region approximately 2 billion light-years across, centered roughly on our local group, within which the average matter density is substantially depressed below the cosmic mean. 2 billion light-years requires contextual framing. The Boötes void, described in the preceding section as so large that its discoverers were embarrassed to report it, extends 330 million light-years. The KBC void is 6 times larger in diameter. It encompasses the Laniakea supercluster, described in detail in the following section, the Shapley concentration toward which much of our local universe is gravitationally streaming, and several hundred million light-years of surrounding space in every direction. The local group, the small ensemble of galaxies that includes the Milky Way and Andromeda, sits embedded within this underdense region. not at any extreme margin, but well within the interior of a structure whose boundaries have been traced through the positions and velocities of thousands of galaxies measured across multiple independent surveys. The reason this matters beyond a simple description of our cosmic address is a crisis that has consumed cosmologists for nearly a decade: the Hubble tension. The two most precise independent methods for measuring the universe's current expansion rate produce values that disagree at a level of statistical significance that should be impossible if both methods are correctly applied. One method leverages the early universe, specifically the acoustic oscillation imprints visible in the cosmic microwave background radiation, to derive an expansion rate. The other uses the distance ladder assembled from calibrated measurements in our immediate cosmic neighborhood to measure the rate directly and empirically. The early universe method produces approximately 67 kilometers per second per megaparsec. The direct local measurement produces approximately 73. The gap between them, expressed in the standard deviation units physicists use to quantify the significance of discrepancies, stands at 5 to 6 sigma. In particle physics, 5 sigma is universally accepted as the threshold for claiming confirmed discovery. The relationship to the KBC void is precise and unresolved. A region of below-average matter density experiences gravitational dynamics that deviate from the cosmic mean. Galaxies embedded inside a void tend to be pulled toward its outer walls. As the void expands and continues emptying over time, this process imprints an additional outward velocity component on the motions of those galaxies. If our location inside the KBC void introduces a systematic upward bias to the measured recession velocities of nearby galaxies, then local expansion rate measurements would register above the true global expansion rate. Not because any individual measurement contains an instrumental error, but because what is being measured locally and what is being computed from early universe physics represent genuinely different quantities. We would be reading the universe through the distorting lens of a bubble, and that bubble would be feeding us the wrong number. Whether the KBC void accounts fully for the Hubble tension remains actively debated. Some analyses conclude that the underdensity is not pronounced enough to explain the entire 5 to 6 sigma gap. Others find that properly modeling the void's influence shrinks the discrepancy to levels potentially attributable to residual systematic effects. What is not in dispute is that our location in the universe's large-scale structure is not a cosmologically neutral fact. It is a physical circumstance with measurable consequences for every quantity our instruments record about the universe's fundamental parameters. The void we inhabit has an outer boundary. Beyond its walls, matter accumulates in the gravitational structures that have been building since the earliest epochs. And the most immediate such structure, the one that contains the Milky Way and approximately 100,000 of its galactic neighbors, received a formal name only in 2014. R. Brent Tully at the University of Hawaii and collaborators published a paper in Nature that year, mapping what they named Laniakea, a Hawaiian phrase meaning immeasurable heaven. The name was selected deliberately. The structure had not previously been recognized as a coherent gravitational entity, because the observational method required to identify it had not previously existed at sufficient scale. Tully's team used a dataset called cosmic flows, a catalog of galaxy distances and velocities assembled through years of careful measurement, to chart the gravitational flow of matter across the local universe. Standard, large-scale structure surveys map the positions of galaxies, recording where things are. Cosmic flows tracked galaxy velocities, recording where things are going. From those velocity vectors, the team reconstructed the gravitational potential landscape that generates them. Galaxies do not remain stationary relative to their neighbors. They move, and the direction and speed of that motion traces the underlying mass distribution even in regions where no luminous matter is detectable. By mapping the velocity field outward in all directions from our position, Tully's team identified the limits of the gravitational basin within which our local group resides and is gravitationally bound to flow toward a common attractor. The resulting structure was a supercluster 500 million light-years across, containing more than 100,000 galaxies, with a total mass equivalent to roughly 100 million billion stellar masses in stars and dark matter combined. The Milky Way and Andromeda sit near its periphery. The Virgo cluster, the nearest major concentration of galaxies to our local group, occupies a position near its center. The entire supercluster's gravitational velocity field trends inward toward a region in the direction of Centaurus that Tully identified as the primary mass concentration, the gravitational focus toward which everything in Laniakea is being slowly drawn. The fact that this structure had never been delineated as a coherent object before 2014 illustrates how genuinely difficult the largest cosmic scales are to perceive. Individual galaxies are observable objects. Galaxy clusters had been catalogued for decades, but a supercluster spanning 500 million light-years, containing 100,000 galaxies within a gravitational basin defined by velocity flows rather than by visible boundaries, requires a particular measurement approach at a particular spatial scale to resolve as a single coherent entity. A subsequent analysis using the fourth iteration of the Cosmic Flows Catalog, published by Alexandra Dupuy and Hélène Courtois in Astronomy and Astrophysics in 2023, incorporated roughly 56,000 galaxy distance measurements and confirmed the Laniakea volume, while further revealing that superclusters identified throughout the local universe are on average an order of magnitude larger than the standard cosmological model predicts they should be. The complication emerges here. Laniakea is already moving toward something. The entire supercluster structure, all 500 million light-years of it, all 100,000 member galaxies, is flowing at roughly 600 kilometers per second toward a concentration of mass in the direction of Centaurus. What it is approaching, and what lies beyond that, is the subject of the next level of description of the architecture we inhabit. Something is exerting a gravitational pull, not only on our galaxy, not only on our local group, not even solely on our supercluster of 100,000 galaxies. Everything within Laniakea, across 500 million light-years, is streaming toward a region of the southern sky in the direction of Centaurus and Norma, at velocities that the combined gravity of every directly observable structure in that direction cannot explain. The entity responsible acquired a name in the 1980s, the Great Attractor. Its existence was inferred from the systematic non-Hubble motions of galaxies across the local universe, velocities that their positions relative to known concentrations of matter could not account for. Some enormous mass concentration, equivalent to roughly 1,000 ordinary galaxies, appeared to be drawing everything within several 100 million light-years toward it. The Great Attractor poses a specific observational challenge. It occupies a position almost precisely in the plane of the Milky Way as seen from Earth. The gas and dust filling our own galaxy's disk absorb and scatter radiation across most of the electromagnetic spectrum, creating what astronomers designate the zone of avoidance, a swath of sky where ground-based and most space-based surveys cannot observe clearly. X-ray and radio wavelengths can penetrate this obscuring band to some degree, and targeted campaigns have mapped portions of the Norma cluster, a dense galaxy concentration near the center of the Great Attractor region. But the complete mass distribution responsible for the peculiar velocity flows measured across Laniakea remained difficult to characterize precisely for decades, because the most powerful available mapping technique, optical redshift surveying, was precisely the one the zone of avoidance blocked. What lies beyond the Great Attractor, accessible to surveys that approach from angles where the zone of avoidance is less obstructive, is the Shapley concentration. George Shapley, the Harvard astronomer who first recognized in the 1930s that the universe extended vastly beyond any contemporary estimate, identified this overdense region but lacked the tools to measure its true extent. Modern surveys have defined it as the densest galaxy concentration in the local universe, a region roughly 650 million light-years from our position, containing mass equivalent to approximately 8,000 typical galaxies, organized into dozens of interconnected clusters, and the dense filaments linking them. Its volume is roughly 10 times that of Laniakea. The peculiar velocity patterns measured across our local universe suggest that many galaxies in our region are ultimately flowing not merely toward the Great Attractor, but toward the Shapley concentration behind it, a gravitational well that has been accumulating mass throughout the entire history of the universe, and whose influence extends across a significant fraction of the observable cosmos. This nested picture of gravitational flows, superclusters moving toward attractors, attractors embedded in larger basins, basins flowing toward still larger concentrations, repeats at successively larger scales until it merges with the cosmic web, where filaments that transport matter toward cluster nodes eventually attenuate, and the intervening voids become the dominant structural feature. Tully invoked the watershed analogy. Matter flows along cosmic channels the way precipitation flows down hillsides. Every galaxy, like every drop of water, belongs to a specific gravitational catchment basin that determines its ultimate destination. We belong to a basin whose final gravitational terminus may be the Shapley concentration, which itself is embedded in the broader cosmic web, which is itself unevenly distributed across the observable universe in ways that continue to challenge every model constructed to describe it. But the velocity measurements those telescopes collected, the numbers encoding the motions of those galaxies, produced an expansion rate that refused to reconcile with the expansion rate derived from the most ancient light in the universe. That disagreement, which has only grown more sharply defined and more resistant to resolution with each passing year of improved measurement, represents what is now the deepest unresolved crisis in the discipline. In 2011, Adam Rice at Johns Hopkins University, Saul Perlmutter at the Lawrence Berkeley National Laboratory, and Brian Schmidt at the Australian National University received the Nobel Prize in Physics for establishing that the universe's expansion is accelerating. That discovery, made in 1998 through precise measurements of Type 1a supernovae at a range of distances, introduced dark energy as the dominant constituent of the universe, the mysterious force propelling galaxies apart at a continuously increasing rate. The measurement that earned them the prize required a precise value for how fast the universe was expanding, a quantity encapsulated in the Hubble constant. From that point forward, determining the Hubble constant with maximum precision became one of the central preoccupations of observational cosmology. Adam Russ continued refining the local measurement throughout the 2010s, directing the SH0ES collaboration dedicated to the supernova calibration of cosmic distances. The method employs a chain of calibrated measurements connecting parallax measurements of nearby stars to pulsating Cepheid variable stars in nearby galaxies to Type 1. A supernovae, luminous enough to be detected across billions of light years. Each rung of the chain is calibrated against the rungs below it, and the total chain extends from our immediate galactic neighborhood outward to the regime where the pure expansion of the universe dominates all local gravitational motions. By 2022, Ries's team had pinned the Hubble constant at 73.17 plus or minus 0.86 kilometers per second per megaparsec. The value derived from the cosmic microwave background radiation measured by the Planck satellite and published with its highest precision in 2020 is 67.36 plus or minus 0.54 kilometers per second per megaparsec. Both measurements are highly precise. They differ by approximately 6 kilometers per second per megaparsec. Expressed as statistical significance, the discrepancy registers at 5 to 6 sigma. For decades, the prevailing hope was that the disagreement would evaporate once measurement errors were fully characterized and eliminated. That hope was directly tested when the James Webb Space Telescope, with its superior angular resolution and light-collecting power, began observing the same Cepheid variables and supernovae in the same galaxies that Ries's team had used with the Hubble Space Telescope. Ries's team published their Webb-based calibration results in 2023. The new telescope confirmed the Hubble Space Telescope measurements with high fidelity. The Hubble constant measured from the local distance ladder read 72.6 kilometers per second per megaparsec, matching the Hubble Space Telescope value of 72.8. Instrumental systematic error had been among the most plausible candidate explanations for the discrepancy, and the James Webb Space Telescope had now effectively excluded it. Restated with the instrumentally straightforward explanations removed from consideration. What remains is the real and consequential possibility that our model of the universe contains a fundamental error. Wendy Friedman at the University of Chicago, directing an independent team employing alternative distance calibrators, including the tip of the red giant branch and carbon-rich Mira variable stars, found that 2 of her 3 methods converged on the Planck value, while 1 matched Ries. Her conclusion was that a systematic error persisted in one of the approaches, though she did not specify which. Ries, whose method has been developed and scrutinized across more than a decade by multiple independent groups, maintains that the discrepancy reflects a genuine physical reality rather than a measurement artifact. The field remains without consensus. What it possesses, confirmed by the most capable observatory humanity has ever constructed, is a genuine, unresolved crisis at the foundational level of cosmological knowledge. On April 4, 2024, the Dark Energy Spectroscopic Instrument Collaboration released results from its first year of operation. The instrument, mounted on the Mayall 4-meter telescope at Kitt Peak National Observatory in Arizona, had spent that year measuring the redshifts of more than 6 million galaxies, generating the most detailed 3-dimensional map of the universe's large-scale structure ever assembled. The survey's primary scientific objective was to measure how the universe's expansion rate has evolved across its history, and specifically to test whether dark energy, the force driving the accelerated expansion, behaves as the most minimal available model predicts. That minimal model is called the cosmological constant. Einstein introduced it in 1917 as a term in his field equations of general relativity that would balance gravity and keep the universe in a static configuration. He discarded it when Hubble demonstrated the universe was expanding. It was restored when Perlmutter, Rees, and Schmidt demonstrated that the expansion was accelerating. In this model, dark energy maintains a fixed energy density at every point in space and at every moment in time. It neither weakens nor intensifies as the universe evolves. It is a property of empty space itself, a constant energy content embedded in the fabric of reality, exerting the same outward force regardless of when or where in the universe it is measured. The dark energy spectroscopic instrument data, when combined with Planck satellite measurements and supernova survey datasets, including the Dark Energy Survey, indicated something different from the cosmological constant's predictions. The combined analysis produced a deviation from constant dark energy at a statistical significance of 3.9 sigma, corresponding to strong confidence that dark energy's behavior has changed over the universe's history. Michael Levi, the project director for the Dark Energy Spectroscopic Instrument, stated that the data raised the concrete possibility that dark energy has been evolving over cosmic time. A separate analysis, published in Physical Review D in September 2025 by Anwar Shajib at the University of Chicago, and collaborators concluded that dark energy had declined in strength by approximately 10% over recent cosmic history at a confidence level of 99.6%. The implications of this result are extraordinary. Dark energy constitutes roughly 68% of all the energy in the universe. Ordinary matter, encompassing every object that has ever been observed, measured, or theorized in the entire accumulated history of natural science, amounts to approximately 5%. If dark energy can change in strength, if the force that governs the universe's ultimate destiny has been evolving throughout cosmic history, then every prediction predicated on its constancy requires fundamental revision. Whether the universe expands forever, whether the acceleration continues without limit, or whether the expansion eventually moderates, is suddenly an open question in a way it was not before the Dark Energy Spectroscopic Instrument released its results. The theoretical machinery capable of generating a dynamical dark energy carries its own demands. The simplest alternative to the cosmological constant is designated a quintessence field, a hypothetical scalar field permeating all of space that evolves gradually over time, either strengthening or weakening as the universe ages. Unlike the cosmological constant, which is inserted into Einstein's equations as a measured quantity with no physical mechanism, quintessence fields emerge naturally from certain extensions of particle physics, particularly theoretical frameworks that incorporate additional scalar degrees of freedom beyond those in the Standard Model. The difficulty is that the quintessence frameworks capable of reproducing the dark energy spectroscopic instrument data require that this field's evolution proceed with extraordinary slowness and fine-tuning, maintaining no detectable variation across the first 10 billion years of cosmic history, before shifting measurably only during the most recent few billion years. Why a dynamical field would mimic a constant for the overwhelming majority of cosmic time and only recently begin evolving in a detectable manner is a question that none of the existing theoretical frameworks address convincingly. But there is something more specific and more alarming in the data than a mere weakening trend. Something that makes the physics of dark energy particularly difficult to accommodate within any established framework. Dark energy's behavior is quantified through a parameter called the equation of state, conventionally written as W. For the cosmological constant, W equals -1 exactly. Values of W greater than -1 describe dark energy that gradually weakens, potentially allowing gravity to eventually reassert dominance and reverse the expansion. Values of W less than -1 describe a category that carries its own technical designation: phantom energy. Phantom energy intensifies as the universe expands. The larger space becomes, the more energy it contains, and the more rapidly it drives everything apart. The expansion accelerates without ceiling, and the growing repulsive force eventually overpowers every other interaction in nature. William Elbers at Durham University and collaborators, analyzing the dark energy spectroscopic instrument data in combination with other survey datasets, detected evidence for something the simplest theoretical frameworks explicitly forbid: dark energy, whose equation of state had crossed the phantom divide. The data implied that dark energy had functioned as phantom energy in the past, with W below -1, but had since moderated and now resided above that threshold. The crossing of that boundary is theoretically problematic because the simplest dark energy models, including the cosmological constant, cannot cross it. They remain on one side of the phantom divide throughout the entire history of the universe. The data appeared to describe a cosmos in which dark energy had done something the simplest theoretical accounts declared impossible. Elbers characterized the situation directly. Dark energy appeared to have been phantom in the past, but was no longer behaving that way today, and the most straightforward theoretical frameworks do not permit that kind of transition to occur. The implication is that dark energy is not a static property of space, but a dynamical entity, something that evolves, whose influence on the universe changes over time. For decades, the standard cosmological picture had written the universe's future with confidence. Expansion continuing forever, accelerating until every galaxy beyond the local group crosses the cosmic event horizon, and the universe cools to maximum entropy across incomprehensible timescales. That picture required dark energy to hold constant. The dark energy spectroscopic instrument data introduced serious doubt about whether it does. The phantom phase, if it was real, carries its own appalling addendum. A universe in which dark energy is phantom does not merely expand forever. It expands at an accelerating rate that increases without bound, and the growing repulsive force eventually overwhelms the binding forces that hold together every structure in nature. Galaxy clusters, galaxies themselves, stellar systems, eventually planets and even individual atoms are progressively dismantled as the expanding repulsion overtakes the forces binding them. This scenario has a name: the Big Rip. The timeline it describes runs as follows. Approximately 2 billion years before the terminal moment, the gravitational bonds holding galaxy clusters together are severed. 60 million years before the end, the Milky Way is torn apart. 3 months before the final instant, our planetary system is dismembered. 30 minutes before the end, Earth is pulled into fragments. In the final fractions of a second, atoms themselves are ripped apart as the force reaches the scale of nuclear binding energies. The current data does not confirm that this terminal future is imminent. The evidence suggests dark energy was phantom in the past and has since moderated. But the fact that the dominant component of the universe has already crossed the phantom divide at least once, that it behaved at some point in cosmic history as a force for which the standard model has no theoretical basis, means that the future cannot be reliably extrapolated from models that assumed such a crossing was impossible. In September 2025, Henry Tai at Cornell University published a paper in the Journal of Cosmology and Astroparticle Physics, introducing a different kind of ending. Tai's analysis focused on the cosmological constant itself, the value Einstein assigned to the energy content of empty space, and argued that rather than representing a fixed positive value eternally driving expansion, it might represent a metastable configuration, a temporary state rather than a permanent one. In his framework, the effective cosmological constant is not truly constant, but emerges from a landscape of possible vacuum energy configurations, and the universe currently occupies one that is slowly shifting toward a different value. The analysis concluded that if the cosmological constant is intrinsically negative at the deepest level of the vacuum landscape, the current phase of accelerated expansion is temporary. Gravity would eventually prevail. The timeline Tai's model generates is specific. The universe is currently approximately 13.8 billion years old. His calculation places the total lifespan of the universe at roughly 33 billion years. The current phase of accelerated expansion would continue for approximately 11 more billion years before gravitational dynamics began to reverse. From that turning point, contraction would commence, slowly at first and then with increasing speed, until everything collapsed back into a singularity in the event cosmologists call the Big Crunch. The end would arrive approximately 20 billion years from now. For scale of comparison, the Sun has approximately 5 billion years of hydrogen fusion remaining in its core. Our solar system would survive into the contraction phase, exist long enough to observe the expansion beginning to decelerate, and would ultimately be compressed along with every other structure in the universe into the final singularity. Young-Wook Lee at Yonsei University in South Korea, whose team examined the expansion history using supernova data published in 2025, found independent evidence that the universe had already entered a phase of decelerating expansion, consistent with a cosmological constant that is diminishing in strength rather than holding at a fixed value. The Big Crunch scenario had dominated cosmological thinking for most of the 20th century, before the 1998 discovery of accelerating expansion appeared to rule it out definitively. Tai's paper and the dark energy spectroscopic instrument results collectively reopened that conclusion. They do not confirm the Big Crunch. They confirm that the answer is genuinely unknown. Whether the universe expands forever, dismantles itself, or collapses back to a singularity is again a question with no settled answer. 3 decades of cosmological consensus have eroded in 2 years of precision measurement. What makes the Big Crunch scenario specifically unsettling is the familiarity of the reference points its timeline intersects. The contraction phase in Tai's model would not announce itself dramatically. It would begin as an almost imperceptible deceleration in the expansion rate, a subtle slowing at first indistinguishable from normal variance in cosmic motion. Galaxies that have been separating for billions of years would begin receding from each other more slowly, then halt, then gradually begin to approach across timescales comparable to the current age of the universe. As the contraction deepened, the cosmic microwave background radiation, the afterglow of the Big Bang that has cooled to less than 3 degrees above absolute zero, and now permeates all space uniformly, would begin to reheat as the universe's volume decreased. The sky, dark across the trillions of years in the other 2 scenarios, would grow incrementally brighter as all the energy that expansion had diluted began concentrating again. In the final stages of contraction, temperatures would climb to thresholds where the boundaries between galaxy clusters dissolved, then where individual stars could no longer maintain structural integrity, then where atoms broke apart into their constituent particles until the singularity arrived. Everything that had ever existed, compressed into a geometric point. The three possible endings now sit before cosmology with approximately equivalent scientific standing. They do not represent distant theoretical possibilities relegated to the speculative margins of the field. They are the three outcomes the observational evidence permits, each supported by distinct subsets of current data, each producing a finality so total that the word ending itself begins to feel semantically inadequate. The first is heat death, sometimes called the Big Freeze, the scenario that held consensus for roughly 2 decades after the discovery of accelerating expansion. Under this outcome, dark energy remains constant or weakens too slowly to alter the trajectory. The universe expands forever. All galaxies beyond the local group vanish behind the cosmic event horizon within 100 billion years. Across the following 100 trillion years, the remaining stars exhaust their fuel, cool, and extinguish. The merged remnant of the Milky Way and Andromeda becomes a diffuse cloud of cooling stellar corpses, white dwarfs radiating their residual thermal energy across billions of additional years. Protons, if the grand unified theories that predict proton instability are correct, decay over timescales of roughly 10 to the 33rd years. Black holes, immune to proton decay, persist longer, evaporating through Hawking radiation over timescales approaching 10 to the 100th power years. After the last black hole dissolves, only the most tenuous residual thermal energy remains, distributed across a spatial volume so immense that the concept of temperature itself approaches meaninglessness. Maximum entropy. No further transformation is possible. This condition persists indefinitely because indefinitely is precisely what remains. The second is the Big Rip. The outcome made physically possible by the phantom energy behavior the dark energy spectroscopic instrument data suggests the universe has already passed through. If dark energy's equation of state returns below -1, the repulsive force grows without limit as space expands. The endpoint timeline, described in the preceding section, counts down from roughly 2 billion years with galaxy clusters disintegrating, to 60 million years with the Milky Way being torn apart, to 3 months with the solar system dismembering, to 30 minutes with Earth fragmenting, to the final fractions of a second when atomic nuclei and the particles within them are separated by a force that has overwhelmed every binding interaction in nature. The universe does not cool into silence. It accelerates through the dissolution of structure, then chemistry, then physics itself until nothing bound persists anywhere. The third is the Big Crunch, revived by Tye's 2025 paper. If the effective cosmological constant is negative at the fundamental level, gravity ultimately overcomes expansion. The universe decelerates, halts, and reverses over the next 11 billion years. The sky brightens as contraction concentrates the cosmic microwave background back through visible wavelengths. Every structure that gravity assembled across the entire history of expansion is progressively compressed. In the final phase, structure dissolves into a fireball of shrinking scale, returning everything to the singularity from which the Big Bang emerged. Each of these endings is absolute. None produces a remnant. None contains a physical mechanism through which any information about what preceded it could survive. The universe will end. The only question is in which specific form that ending arrives. And that uncertainty is not a narrow gap between near-identical predictions. It is a three-way split between cold eternal stillness, violent structural dissolution, and total gravitational collapse, governed by the behavior of a force comprising 68% of all the energy in existence. A force we are not yet able to characterize precisely enough to distinguish between those outcomes. The James Webb Space Telescope entered scientific operation in mid-2022. By early 2026, 3.5 years into its primary mission, it had generated results that demanded revisions to the standard model of cosmic evolution, confirmed a fundamental measurement crisis in the universe's expansion rate, detected chemical signatures in the most distant confirmed galaxy that required entire generations of stars to have lived and died before any of those stars were theoretically expected to have formed, and catalogued a population of black holes so massive and so early in cosmic history that no accepted physical mechanism could have produced them on the available timescale. It had shown the five-way galaxy merger at 800 million years, the hypervelocity star departing the galactic center at 6 million kilometers per hour, and structures in the cosmic web that exceed the maximum coherent size the cosmological principle permits by a factor of 8. None of these findings generated terror through spectacle or scale. They generated something more precise and more lasting. The specific intellectual discomfort of recognizing that the theoretical framework used to understand the universe, a framework that had survived every observational test applied to it across 4 decades, was systematically failing in ways not yet fully characterized. Every measurement designed to confirm the model confirmed the crisis instead. Every anomaly that earlier observations had flagged as potentially resolvable by better data became less resolvable, not more, as the data improved. The telescope did not show us that the universe is large. We already knew it was large. It showed us that we had been wrong about what the universe does, and it has not yet shown us how deeply that wrongness extends. This is the precise character of the fear. Not scale, not distance, not the smallness that raw numbers produce in human perception. The fear is the specific recognition that our understanding is preliminary in ways we are only now beginning to measure. Humans have been aware of the distances to nearby galaxies for a century. Edwin Hubble's measurements in the 1920s established that the Milky Way is one galaxy among billions in an expanding universe. That knowledge has been absorbed into the background of educated culture. It fills textbooks, narrates planetarium programs, appears in introductory astronomy courses. The distance to the edge of the observable universe is a familiar figure. Familiarity is not terror. What the James Webb Space Telescope added was foundational uncertainty. The Hubble tension is not a measurement of how vast the universe is. It is a measurement of how well we understand it. The answer, confirmed by the most precise telescope ever built, is that we do not understand it well enough for both of our most precise and carefully checked measurements to be simultaneously correct. Dark energy comprises 68% of all the energy in the universe, may be evolving, and we do not know what it is at. The most basic physical level. The structures the telescope reveals in the early universe appear at scales and densities the standard model does not generate. The cosmological principle, the foundational assumption of homogeneity underlying all of modern cosmology, confronts a structure 10 billion light-years across that violates it by a factor of 8 with no identified observational error. The fate of the universe is genuinely undetermined between 3 scenarios, each of which terminates everything that exists. The terror is not that the universe is large enough to render us insignificant. The terror is that the universe is strange enough to render our understanding of it provisional. We occupy a planet orbiting an intermediate mass star in the outer regions of a galaxy that is itself a peripheral member of a supercluster gravitationally flowing toward an attractor we cannot fully observe. We are embedded in a void 6 times larger in diameter than the most extreme void previously known. We inhabit a universe whose expansion rate we cannot reconcile between our 2 most precise methods of measurement, whose dominant energy component we cannot identify, whose earliest history does not conform to our models, and whose ultimate fate remains genuinely open between 3 scenarios, each of which terminates everything completely. Against that backdrop, our species has existed for perhaps 300,000 years. We have possessed instruments capable of measuring any of these quantities for perhaps a century. We have had the specific instrument needed to read the oldest light in the observable universe for 3.5 years. The window during which the universe's complete history remains legible in the sky will close within roughly 100 billion years. That duration sounds vast until it is set against the fact that the universe has already existed for 13.8 billion years and will persist for, at minimum, 33 billion more. We arrived late in the only era when the full archive of cosmic evidence was accessible, constructed the precise instrument needed to read it just as the window was beginning to narrow, and discovered when we looked that everything we believed we understood required reconsideration. The James Webb Space Telescope did not reveal that the universe is terrifying because of how large it is. It revealed that the universe is terrifying because of how incompletely, after everything we have accomplished, we have understood it. What we are able to observe in this brief interval of cosmic legibility is sufficient to know that the questions we cannot yet answer are the ones that matter most, and that the instrument currently pursuing them will not continue long enough to resolve all of them on its own. The universe will continue operating according to rules we have not fully identified, at scales we cannot fully observe, toward an ending we cannot yet determine. We are present for only a fraction of the time it takes for any of that to unfold. The records this telescope has opened will not close with its eventual decommissioning. Every spectrum it captures, every galaxy it confirms, every chemical signature it extracts from light that has traveled for billions of years becomes part of a permanent archive. The next generation of instruments will inherit those measurements and push beyond them, carrying forward the questions the Webb has sharpened rather than resolved. What makes this moment singular in the history of science is not merely that a powerful new telescope is operating. It is that the telescope arrived precisely when the accumulated weight of precision measurement had begun exposing the limits of the framework built to explain what those measurements should find. The crisis and the instrument arrived together. The questions the Webb has opened are not puzzles at the margin of a mostly complete picture. They are fractures running through the foundations. And there is something both humbling and irreplaceable about being the generation that first saw those fractures clearly enough to know their depth.